welcome to another AQA AS chemistry video. Today I'm going to be just doing another video on questions to do with the mass spectrometry and electron configuration questions. So mass and isotope numbers, that type of question. So this is another past paper that I've got. So now that we finished the first section of AQA AS physical. I want to just do this one practice paper. It pretty much is. It's not all of it, but I just want to, this is like an example. If you can do this type of questions, then you can do the rest of year one physical. The first section of physical chemistry should be no problem to you. So this is a 57-minute paper. I'm going to try and spend, well, it's 57 marks. I like to do a mark per minute. I know they give you a bit more, but I've always practiced a mark per minute. So yeah, I'm going to go for it. I'm going to try and do it for 57 minutes, but at the same time, I want to try and explain what's going on so you can kind of like understand why as I'm doing it. So it's probably going to go over 57 minutes, but I'm going to do a timer here. I'll do a timer here to show you that I'm trying to do it in exam conditions. Yeah. So I will start now. But I'll try, if I go over it, just know that I probably could do it in 57 minutes, but I'm just trying to explain to you how I'm doing it as I'm going through. So, but if you're doing it by yourself, try and do it within 57 minutes. All right, and do I have my periodic table with me? Yes, all right. 3, 2, 1, go. All right, so beryllium is an element with atomic number of 52. Using the information from the periodic table, complete the electronic configuration of beryllium. And it started from krypton. Now, these type of questions, they usually, so if you can actually, as I showed before, I showed you how to do electronic configuration before, but if it's really big, you can actually just go to a noble gas and just write the name of a noble gas to where he, to save you writing all the way up to that number. So from 52, I think krypton has 36, krypton has 36 of those electrons already, so we don't have to actually write. We only have to do the remainder of 52 minus 36, whatever that is, and from that point onwards. So that's one of the benefits of just writing the krypton here. So to still though, if I was still writing this, although I do it like this, this is the first thing I'm doing. 3s2, 4s2, 5s2, and 6s2, just in case. That's 2. It shouldn't be crossing through, sorry. 4. That's 10, 12, 18, 20. 30, 36, and that's 38. So krypton is 4p6. So after 4p6, that's krypton. And then 5s2, so we need to go from, so faster to, just do that quickly. I need 16 more electrons, so 5s2, 4d10, and then a 5p4, and that should be enough. All right. Use the graph to calculate the relative atomic mass of the sample of beryllium. Give your answer to one decimal place. Remember that equation that we have before? You'd get each individual one, the mass to charge ratio, the M of it, of that isotope, times by the abundance. They haven't given, basically the abundance would be in a ratio, either in a ratio, percentage. They've given us it in, if we count each block as a 1 or like a ratio, so we can use it as saying 124. Let's say each one represents 1. It's 124 by 2. Bad. Plus 126 by 4 plus 128 by 7 and 130 times by 6. That's all. If you add 2 plus 4 plus 7 plus 6 together, that's 19. And if you just do that, all of that over 19, you should get, let's do it here, 124 by 2 plus 126 by 128 by 7 plus 130 times by over 19. 127. They set to one decimal place. That's what really important here. Make sure to highlight that during the exam. I haven't got my highlighters here, but just try and make sure to do that. They do allow you can use highlighters in the exam. But it'll be 127.8. That's the final answer. In case they don't, you can always put a box around it just to make sure they see it's 127.8. Just what might cause the relative atomic mass of the sample to be different from the relative atomic mass given in the periodic table. In the actual periodic table, there'll be other isotopes. So there are other isotopes of beryllium. That's what I would say. There's way more. If you actually look at a mass spectrum, there's many more, not just these ones. There are other isotopes of beryllium present. I say beryllium present. Sorry, I keep saying beryllium. It's tellurium. No, I keep saying beryllium. Tellurium. All right. How are we doing for time? 4, 5. Not too bad. Just spending a minute now. Write an equation for the reaction that occurs when tellurium ion hits the detector. So when the ion hits the detector, it's a positively charged ion first of all. Tellurium is in the gas phase. It's in the gas phase and is positively charged, and then it would gain an electron to form a tellurium atom again. State the mass charge value of the ion that produces the biggest current at the detector when the spectrum in the graph is recorded. Give a reason for your answer. You have to understand what they're trying to ask you here. The one that produced the biggest current is one that has the highest abundance, right? So the one that has the highest abundance is the one with 128. So the mass charge value would be 128. And the simple reason is it has Te128 has the highest abundance. The mass spectrum of tellurium also has a peak or mass to charge ratio of 64, and explain the existence of this peak. So if you were to look carefully, 64 is actually exactly half of 128. So in my mind, this means that there has been a 2 plus ion that's formed at some point from this 128, from this tellurium 128. So there must be a 2 plus ion formed. I haven't done these questions. I haven't done this since when I was in school, so forgive me if they do end up being wrong. Hopefully they are correct. But there must be a 2 plus ion formed from a Te128. Sorry, on this side, Te128 atom. Predict whether the atomic radius of Te124 is larger than, smaller than, or the same as the atomic radius of Te130. Explain your answer. Predict whether the atomic radius of Te124 is larger than, smaller than, or the same as the atomic radius of TE130. They should be the same. They're I'd say the same. Because they're just isotopes of one another, so they are, yeah. The isotopes of the same atom. So the nuclear charge is the same. If so, what causes a ion to become bigger or smaller is like when you're going across a period, it's the proton number, the nuclear charge. The nuclear charge, number of protons is the same, so there will be there's no change in that there's no change in that electrostatic attraction. It's the same. Your compound's a bit heavier, I guess. The nucleus is a bit heavier with the 130, but the actual charge is the same because neutrons are neutrally charged. So I say they're the same because they're isotopes of the same atom, so the nuclear charge is the same. So atomic radius would be the same. A sample of sulfur consisting of 3 isotopes has a relative atomic mass of 32.16. The following table gives the relative abundance of two of these isotopes. Use this information to determine the relative abundance and hence the mass number of the third isotope. Give your answer to the appropriate number of significant figures. We've done this type of question before, so it's not going to be a problem for us. So using the relative abundance, hence. Okay, so first of all, we know it's going to be out of 100%, and we know there's only 3 isotopes of them, so we just do 100 minus 91 minus 1.8, which should be, if that's 9, 8, 7.2, all right, 7.2%, and we just do 32 by 91 plus 33. You don't have to do as a percentage, you could just do 0.91, but I'm doing it like this. 1.8 plus 7.2x all over 100 is equal to 32.16, right? Very easy, you can already see what's going on here. I just add these together actually, so 32 by 91 plus 33 times by 1.8. 2971.4. So 2971.4 plus 7.2x is equal to 3216. 7.2x is equal to 3216 minus the answer, and that is 244.6. X would be equal to 7.2 over 244.6. 7.2. And that's 33.9. It's like it's the appropriate number of significant figures. If you're doing the mass of the isotope, they're all in 2 significant figures here. So I'll be saying X is equal to 34. Describe how ions are formed in the time of flight mass spectrometer. So there's 2 methods, electron spray ionization or electron impact ionization. I'm going to do, say, electron spray ionization. Dissolve compound in a polar solvent. And then you would apply a high voltage to this polar solvent. It said describe, not explain, so I say apply a high voltage to the polar solvent. And then then a proton is removed is removed from solvent and gained by, I say an atom? I was it by the molecule, I say. A proton is removed from the solvent and gained by an atom to form a positive ion. Alright. A time-of-flight mass spectrometer can be used to determine the relative molecular mass of a molecular substance. Explain why it's necessary to ionize the molecules when measuring their mass in the time-of-flight mass spectrometer. And that's because the molecule needs to be positively charged in order to be accelerated by an electric field. Wait, did it say molecule? Okay. I wouldn't say this. I mean, just thinking, if you said, I think this is a I still don't know if I should call this an atom or a molecule. Come back to this one. I feel like I should call that a molecule, but I haven't got anything to say there. But anyway, so the molecule needs to be positively charged in order to be accelerated by an electric field, and for it to be attracted to and collide with the negatively charged detector plate. To induce a current. Which of these atoms has the smallest number of neutrons? Smallest number of neutrons, alright, so my question, so that has 2, 2, 3, 1. Alright, state the meaning in terms of the mass number of an isotope, it's the total number of protons and neutrons in a nucleus. Alright. Give the symbol of the element that has an isotope with a mass number of 68 and has 38 neutrons in its nucleus. Alright, so 68, mass number 68. 68 minus 38, 30. Zinc. Right, the following shows a simplified diagram of its mass. Just at the symbol, I have to write, yeah, okay. The following shows a simplified diagram of a mass spectrometer. What happens to the sample in parts P and QP? I'd say ionization. Q, acceleration. In a mass spectrometer, the isotopes of an element are separated. Two measurements of each isotope are recorded on the mass spectrum. Say two measurements that are recorded of each isotope. So say the mass, I'd say the mass to charge ratio definitely. And they only measured the mass to charge ratio and the abundance. The sample of element R contains isotopes of mass numbers 206, 207, and 208 in the ratios in its 1:1:2 ratio of abundance. Calculate the relative atomic mass of R. Give your answer to one decimal place. Okay, so you already know what to do with these. So just 206 plus 207 plus 208 times by 2, because we're following this 1:1:2 ratio, over 4, and that gives you your answer really. That's it. I mean, 206 plus 207 plus 2 by 208, and that's over 4. 207.25. 1 decimal place, 207.3. I should say approximately. Well, yeah, 207.3. Great. Identify R. 207.3. That's lead. The closest one there is lead. I'd say lead. All of the isotopes are react in the same way with concentrated nitric acid. Say why the isotopes of an element have the same chemical properties. The chemical properties are always determined by the electronic configuration. It's because they all have the same. So they all have the same electronic configuration. Great. Alright, the mass spectrum of the isotopes of element X is shown diagram. Define the term relative atomic mass. It's the average mass, I would say, of an atom relative to 1/12 the mass of carbon-12. Yes. Use Venn diagrams to calculate the relative atomic mass of X. The relative atomic mass of X, so that's just going to be... Alright, we already know what to do these questions. 70 by 3. A lot of these questions are quite repetitive in terms of the way, in terms of the type of question, but practice is the only way you can do these questions correctly. 72 by 4 plus 73, and then, I don't know, what was the last? It would be 74, right? 74 by something. Five, right? And then all over, that's 8, 13, and then sorry, I should be doing it here. I could just already do that as 210, but that plus 72 by 4, and then plus 73 plus 74 by 5, all over 13, 72.4. Identify the ion responsible for the peak at 72. 72. Let's actually go and use it's germanium first of all. And it'll be positively charged. because it's an ion, remember if we're going using the mass spectrometry, 72. Alright. Identify which one of the isotopes of X is deflected the most in the magnetic field of the mass spectrometer, and give a reason for your answer. The one that's deflected the most, usually the one that's the lightest. The one that's heaviest doesn't deflect that much. So the lightest one, which is 70, yes, 70. The isotope, I say G70. I'd go like this isotope, G70. It has the lowest I can't write mass to charge ratio. Alright, calm. In a mass spectrometer, making sure that this is in line with this. Sorry. Still got time. In mass spectrometer, the relative abundance of each isotope is proportional to the current generated by the isotope of the detector. Explain why this current is generated. So, when the ion collides with the detector, there's a transfer of electrons from the detector plate electrons. Okay, from the detector plate to the ion. Let's say an electron. There you go. My handwriting is probably poor and you probably can't read it, but that's I'm saying it out loud. But be better than me. Have good handwriting. X and Z are different elements. So I've put these part here. X and Z are different elements. Something there. I think this is a typo in terms of the way it's been presented. Explain why the chemical properties of X70 and Zn70 are different, because they have different electronic configurations. They're different elements. The isotopes, neutrons, but the part that actually matters is the electronic configuration. So they have different electronic configurations. A sample of ethane dioic acid was treated with an excess of an unknown alcohol in the presence of a strong acid catalyst. The products of this reaction were separated and analyzed in the time of flight mass spectrometer. The two peaks were observed at mass charge ratio of 104 and 118 to identify the species responsible for the two peaks. Right, so ethane dioic acid, how much is that outside? Do this in pencil, don't follow me. 24, 64 plus 2. So 24 plus 64 plus 2, that's 90. And it needs 14. How am I going to, that's going to be a methyl of some sort. So it's going to, if it's an unknown alcohol, be a methanol, right? But then when that collides, then it would just be like this. Surely, right? So HOCO. That's 89 plus 15. Yes. Gonna be, yep. Okay, good. And then it's gonna be a positive charge because it's an ion, of course. Yeah, there'd be that. Can I just write it as that? I mean, I think I have to. Would they allow me to draw it out? I should know this. I haven't done these exams in a long time, so please bear with me. Bear with me. I'm just gonna draw it out. So I have to like HOC. If I'm wrong, if you ever go to the mark scheme and find the mark scheme, and then, they show it, and I mean, it should be. I'm just gonna write out the formula of it just in case. Just in case. And then for the next one, it would be, so that's going to be 28. 28 can have a, okay, that, 24, 25, 26, 27, 28, 29. I think I can get away with that. That's, wait, 24, 25, 26. Yeah, 89%. I think this is it. If I just make that a, wait, it's the same unknown alcohol. So it can't be that. It has to be the same one. So then, if I just had two of these, 15, that's 30. But that's 88. And then 88 plus 30, 118. Yes, okay, good, yep. It'll be H3C, right? I think, yeah, because this must be the only way that you do it. And then that. Or I could write that as, I've really messed up the way I've written here, but hopefully they allow this. But if I haven't got spaces, I just write it like that then. And 118 mass to charge ratio. Hopefully they give you more exams than the actual exam. These ones don't actually replicate in terms of the spacing that they give you. But that's the thing. How much time have we got now? 24 minutes to answer 4. We actually got 12 minutes to answer 24 minutes to answer 12 marks. We set ourselves in a good position actually. So outline how the TOF mass spectrometer is able to separate these two species to give 2 peaks. So firstly, the ionized. It's 4 marks. So I tried to separate this into four points, right? So 2 species are ionized by electric ionization. The two ions are accelerated under an electric field or by an electric field. They have the same kinetic energy, but the speed is determined by their mass. So how I would work that is that to have the same kinetic energy, the ion with a mass to charge ratio of 104 will travel faster, will have a higher speed as it's lighter than the ion with a mass to charge ratio. My handwriting is terrible. 118. But they still have the same kinetic energy. And so the last part say that. So the ion with a mass to charge ratio of 104 will hit the detector plate first. Collide with the detector plate first. Table 1 shows some data about the fundamental particles in the atom array. Last stretch. 20 minutes, 20 and a half minutes to 8 marks. We see speeding through this right now. Table 1 shows some data about fundamental particles in an atom. An atom of hydrogen can be represented as H1. Use data in table 1 to calculate the mass of a hydrogen atom. 1 proton, 1 electron, right? No neutron. So 1.6725 times 10 to the power of minus 24 plus 0.0009 times 10 to the power of minus 24 equals, alright, 1.6734 times 10 to the power of minus 24 grams. Which one of the following is a fundamental particle that would not be deflected by an electric field? That's easy, no charge on a neutron, so it's B. A naturally occurring sample of the element boron has a relative atomic mass of 10.8. In this sample, boron exists as two isotopes, B10 and B11. Calculate the percentage abundance of B10 in this naturally occurring sample of boron. Right, okay, we've done this question before as well, haven't we? So, right. 10x plus 11y over 100 equals 10.8. X plus y equals to 100. They said they wanted to be 10, so I'd call y is equal to 100 minus x. Separate this to this side actually. 10x plus 11, 100. We can substitute this y. If you watch my previous video, we can just use a bit of algebra here. If x plus y is equal to 100, right? Because the abundances should equal 100%, and the abundances are add together to make 100%. We could rearrange the equation so that y is equal to 100 minus x, right? We know that there are different abundances here, x and y. Y is equal to 100 minus x. Therefore, I can substitute this into our equation here. So 10x plus 11 times by 100 minus x, because that's also the same as y, equals, and if I just times this 100 by 10 by 1080, right? Don't worry, it'll give you more space in the actual exam. 10x plus 1100 minus 11x equals 1080. Minus x is equal to minus 20. X is equal to 20%. That x is terrible. I only learned recently that people write x like that. That's a much better way of writing x. So much more professional. Oh, I'm wasting time now. I've got so much time in this. But x is equal to 20%, right? State in terms of fundamental particles why the isotopes B10 and B11 have similar chemical properties. They have the same electron configuration. Complete table 2 by suggesting a value for the third ionization energy of boron. Third ionization energy of boron. So boron is in group 3 in our periodic table, which means that it's after group 3, so the fourth ionization, where it would be the massive jump. You see, there's a massive jump between here and here. And then this is just be a very small jump from here to here. And I say, I can go for 5,000, right? It's not a bad shout. And it's this is right. There should be a massive jump between here and here, because that's the last electron. There's only 3 electrons in the outermost shell. So that's what I'd go for there. Write an equation show the process that occurs for when the second ionization energy of boron is measured. Include state symbols in your equation. Second ionization energy. So remember, I always have to remember it's for boron. What's it say for boron? Boron is, it's going to be that's always going to be in your product. Explain why the second ionization energy of boron is higher than the first ionization energy of boron. Because you're removing an electron from a positively charged ion. And that's it. 14 minutes, 28 it was. 14 minutes and 28 seconds left to spare. And that's going over. Now, obviously in the real exam, you get much harder questions, so you have maybe less time, but this time we just spent over, now going over, looking over things that make sense, or other isotopes, maybe improving your handwriting, I guess. If you're, hopefully you're not as disabled as I am, so you should be fine. The isotopes are the same atoms, so the nuclear charge is the same. 34 electrospionization. Pour solvent, a proton is removed from the solve. Dissolve compounds in the polar solvent, yes. Apply high voltage to the polar solvent, yes. Proton is removed from the solvent and gained by an now this is what I said, I put an asterisk here. I just say atom. They haven't given us anything to say ions. I'll go for that. You know, man, this is giving me way too much. My OCD by a sample molecule / atom. Alright, come on. And for it to be attracted to the colliding negatively charged detector plate, the inducer charge, total number of protons and neutrons in a nucleus. Yeah. Ionization, acceleration. Average mass of an atom relative to one total mass of carbon-12. Has lowest mass to charge ratio when there's a transfer of an electron from the text plate to the ion. Ionization, the ions accelerated by an filter. Energy have higher speed is higher than, so it's lighter than the iron. I'm just going over as you should do. So this is how you should be doing it in exams. Like, just going over things that you have. So if you have lots of time over, you would just look over your last questions, and this page was just generally make sure you don't make any stupid mistakes or any small corrections, just to make sure that you gain the mark. And that's it. I still have 10 minutes left to spare. Hopefully this video was helpful. I'm going to end it here. If you don't find it useful, I'll stop doing them, but I don't know, man. I'll just, if you ever need it.